30. However, if needed, I can stay longer on if there are questions that if we run out of time, I can just stand and answer questions. So yeah, what is Geolab and why do we have Geolab? So what we are seeing in Europe and also worldwide is that the critical infrastructure is more and more threatened by all kinds of threats, like climate change, extreme weather, geohazards, aging, but also the way we use this critical infrastructure. And I think a good example, of course, is the whole energy transition. So there's a big change in how we use the energy infrastructure. But also, for example, in the transport sector, the way we use our roads and our railways are completely different than, let's say, 50 years ago. So there's a lot of things happening in the critical infrastructure, and we need new solutions for that. And so we need scientific research, innovative solutions that to deal with these threats to the critical infrastructure. And to do this proper science, you really need research infrastructure, physical research infrastructure that can support scientific research and innovative solutions. And basically, that's the whole core of the idea behind the Geolab project. So we want to enhance Europe's critical infrastructure, and that's the motto of the project. And we're dealing with several types of critical infrastructure, like transport, urban, water, and energy. It's shown in this yellow part. And we want to develop our knowledge and develop solutions. So there are a number of examples of knowledge development. So develop knowledge on the impact of climate change, extreme weather, and geohazards, the aging mechanisms of soil and structures, the integral behavior of a critical infrastructure system. These are all knowledge developments, and we are also looking at technology solutions. So like the application of new construction materials, implementation of new building methodologies, new design approaches using data and numerical modeling. So Geolab is a collaboration of 10 partners who all have a certain type of research infrastructure. And we are talking about geotechnical environmental research facilities. And within our consortium, we have 5 centrifuges. We have the Deltares centrifuge, the University of Gustav Eiffel, TU Delft, Cambridge, and ETH. These are all different types of centrifuges that are complementary to each other. For example, at TU Delft, we have a very small centrifuge for testing a large series of tests easily. And for example, at Cambridge University, we have a really big beam centrifuge. ETH has its drum centrifuge, but they are also developing now a new centrifuge that will be operational this year. That is also available. And then we have at Deltares and Gustav Eiffel also 2 5.5 meter centrifuges. But we also have other types of research infrastructure in Geolab. So we have, for example, the geomodel container at Deltares, but also the SIDEX railway track simulator, where you can simulate a whole railway track on 1:1 scale, including also the subsoil and the subgrade of the railway track. We have at TU Darmstadt a geotechnical test pit with large dimensions, 5 meters wide, up to 3 to 6 meters deep, where you can build a model. At the University of Maribor, we have a small scale traffic road simulator. And in Norway, we have a number of geotechnical test sites. And what you can see is that we are able within Geolab to do tests at a small scale up to at field scale. So what are we doing in the project? We started the project approximately 2 years ago, and these are the activities that we have in the project. First of all, we have the joint research activities where we develop all kinds of deliverables for example, guidance of transnational access, but also innovation and data management. One of the goals of Geolab is also to share the results of experiments to the wider community, so that the result of an experiment, the data set is well stored and is also reusable. The other activity is networking activity. So we're building a virtual community. We have already a big LinkedIn group. We're still working towards reaching out to other new users, and also having a special innovation management part where we try to connect to the industry to build solutions. What's also a nice thing about Geolab is that we have a focus on next generation researchers. So we try to involve them in experimental work in the form of training programs and internships. One of the core things, and I think that's also one of the main topics of this webinar, is transnational access. We have in the budget of the project, we have sufficient funding for performance on transnational access. So we invite user groups within Europe, so universities, research institutes, critical infrastructure owners and operators, and SMEs. We all invite them to come up with proposals to use this Geolab research infrastructure. And this is supported from the project, and it's not only the use of the research infrastructure, but it's also the technical assistance for operation of the infrastructure, and also the scientific support to help you to build an experiment. So we are now at the third round of transnational access. You see here an overview of the projects that were selected during the first round of the first round of transnational access. And where you see that marked in green are the projects that already have been completed, and some of them will be shown in the next part of this webinar. These are the results from the second round of transnational access. So these are projects that are ongoing, will be performed this year. We had 26 proposals during the last round of transnational access, of which 11 were awarded access. So talking about the transnational access call that's now ongoing, the third one, we have selected the team experiments to validate advances in numerical modeling and data science, leading to a better engineering design. So we are inviting you to bring proposals to the table that fit with this theme of the call. This is funded from the project, as I said, and the submission deadline is on September 30. So there's still time, but yeah, we say if you have an idea, get in contact with the facility manager, the facility you would like to use, and discuss with them your idea in an early stage in order to see if it's feasible to do the experiment that you are thinking of, and to get guidance on how to develop your proposal. So it's an open invitation to do that. There are also some restrictions in transnational access. First of all, the user group should be for the majority from the EU 27, plus the associated countries. So international collaboration is possible, but only at a limited scale. And user group should be from another country than where the facility is. So for the Netherlands, for example, for our facility here, we need to have proposals coming from outside the Netherlands. We have a selection procedure. It's on the website. It's called the access policy, where we describe how the whole selection procedure works, how we evaluate what are the criteria. In the end, the selection is performed by an international user selection panel. This is a group of about 10 to 15 experts that we involve in the project and that make the final selection of the project that are awarded access. Talking about joint research activities, we have done a lot on that up to now. So we have a complete description of the Geolab research infrastructure and also a user manual. We have reports on experimental challenges and technology readiness, where we go into what are the challenges for the research infrastructure, what new technologies are available. We have results on the physical modeling of impact of climate change, reports on joint standards and software protocols to allow easy exchange of data. And what's coming up in the program also, which is an upcoming deliverable that will be finalized this month on high spatial density measurements of 3D laboratory experiments. The idea behind that is that numerical analysis advancing, numerical models become more complex and a higher resolution. And we are looking for measurement systems that can match this higher resolution of numerical modeling. So that's why we need this kind of high spatial density measurements. Some progress is made there, and Suzanne will go into that later on. Regarding networking activities, we had our second Geolab networking event in November last year, hosted by ETH in Zurich, with interesting workshops. But what may be more interesting to mention is that we will have our next networking event in Oslo, hosted by the Norwegian Geotechnical Institute. And this is scheduled for the end of November, 27 November until 1 December. What's also interesting to mention is that at the end of 2024, Deltares and TU Delft will host the European Conference on Physical Modeling in Geotechnics. This will be a collaboration between Geolab and the Technical Committee on Physical Modeling. And it will be an interesting program here in Delft. As I mentioned before, we have a focus for the next generation of researchers. We organized 2-day training workshops for them, where we have our best experts on physical modeling presenting and teaching. The last one was in Zurich with 40 participants on campus and 15 funded from the Geolab project. Participants online, and the recordings are available in the knowledge platform. Next training, of course, will be in NGI, at NGI in Oslo. So I just want to point out our website, where you can find a lot of information on the call for proposals, but also on our research infrastructure. And if you go into the knowledge platform, you find all these reports and deliverables to have a look. Also, recordings of previous activities are available there. So it's a good way to learn more about Geolab and the research infrastructure, and can be used to develop your proposals. Thank you, and let's get started to the next one. Okay, stop sharing. So we are going now to the second session of the Geolab webinar. The first one is a presentation of a completed project. It's called PEPSTAR, Piled Embankments with Basalt Steel Reinforcement, and this will be presented by Mark Snyder of TU Darmstadt. Mark, you can go ahead.
Yes. Okay, thank you for the introduction. Do you see my presentation in full screen?
It's okay.
Yeah.
Okay, great. Okay, then hello and welcome to this presentation about the TA project PEPSTER. PEPSTER being the acronym for piled embankments with a basal steel reinforcement. And I will talk about the large-scale test that was performed here at TU Darmstadt. First of all, I want to show you the real-life situation that we are modeling. So here you can see a common soil with low bearing, typically softer soils at and toward the top. And the deeper you go, you will eventually reach bearing soils. And if you were to construct an embankment on this type of soil, you would see large deformations and uneven deformations, settlements. So to improve the situation, we can make this embankment a piled embankment, one part of which, of course, is the piles. Piles are used to transfer the mostly vertical loads to the lower laying bearing soils. And additionally, you can use basal reinforcements to reduce horizontal stresses, which would cause horizontal deformations or horizontal forces on the piles. So to create our model tests, we took a part of this embankment. We created or we altered an already existing test setup at Deltares. We performed a series of small scale tests. So you see the human to scale. And this other figure of the large scale test is also in scale to the other. The focus of our research was, of course, the influence of the steel reinforcement, which is the biggest change. So it has a higher bending and tensile stiffness compared to, for example, geogrids, geosynthetic reinforcements. Also, we assumed these piles are usually assumed to be supported rigidly, and we made a flexible support to see the influence of that. And of course, the whole operation to see if it can actually be scaled down, what you have to watch out for. Okay. So this here at the top left, you see, you already saw in the photos, this is the geotechnical test pit here at TU Darmstadt. And of this large pit, we took this small piece that you can see in the photo. The 3 meters depth were enlarged with a formwork that was placed on these walls, on these outer walls, to allow a total setup height of 5.5 meters to fit all this in. And so here you can see in the test setup, just as you saw in the embankment, you have a soft soil that is here below, and the piles are founded more rigidly on a more bearing soil. We have the basal reinforcement in blue. We have the embankment body itself made up of sand. And of course, we have a lot of measuring instruments. I will show a small presentation, animation, that shows you that the installation procedure is at the same time also the test procedure itself. So as in the picture before, you see the soft soil having settlements while the embankment is constructed, the grid deforming, and we also watch the surface deformation while we perform the tests. Now I want to talk about the elements of our test setup, and I want to start with the piles. So here you can see in the center photo, you can see the base of the test setup, and you can see the piles sticking out by about 1 meter. You see here at the pile top, we have roughened the surface a bit to model in situ concrete. In total, so including the space below this second floor, we have 2.5 meters of piles per pile. And this is the flexible base that I talked about. So these are springs that allow small settlement for the forces acting. And why do we need this second floor? I will tell you now. So we constructed this setup of hydraulic jackups at the very bottom, then a series of steel beams on top of that. The finish was really thick, 10 centimeter thick wooden plates with holes for the piles that you see in the bottom right. And then a rubber granulate to model soft soil behavior. And also this whole setup is part of the soft soil model, because these jackups that you see on the left, they are initially, before the test was performed, extended by 220 millimeters and can be lowered at the end of the test. So we reduce the subsoil support even more create even more settlement in the soil. The sand, so the embankment body itself, it was pluviated with the pluviator that we have here at Darmstadt that you see in the center image, and we achieved quite a high density. The main difference for this test is the steel reinforcement. We have 3 parts of the steel reinforcement. You see in the left half, it's one continuous sheet. In the right, it's with a bit of an overlap between those 2 sheets, and these 2 halves to each other are just on contact. And they are connected by these hooks you see in the right image, and some of them even have strain measurement. More about the measuring instrument we used. So these are the glass fiber instruments that we used. In its simplest form, it can contain one single strand of glass fiber that enables us to measure the strain along the whole sensor. And in this more advanced form that you see here, those black bars, they contain 4 strain measurements that you can derive deformation from. Also, we had a lot of pressure cells. So these photos that you see, they are slightly above the reinforcement now. And we use them to investigate the load transfer mechanism that you can also see depicted here. So there will be a load transfer to the piles, and we are observing this. Okay, that is my presentation about the PEPSTER test setup. Thank you very much.
Thank you, Mark. Very interesting presentation. Yeah, if you have questions, put them in the chat and we will deal with them at the end. So let's move on to the next one. So Stefan Ritter of NGI will present the Clarifier project, centrifuge modeling of peat embankments. Stefan, go ahead.
Thanks, Don Peter, for this kind introduction. Do you see my slide in presenter view?
Yes, okay.
You can see them, perfect.
Yeah.
Well, thanks for inviting me to present the Clarifier project, which stands for Centrifuge Modeling of Peat Embankments for Critical Infrastructure in Europe. The Clarifier project team consisted of the UC Dublin, which was in the lead of this project, and the PI was Mike Long. Then the Technical University of Science in Trondheim, in Norway, then the Norwegian Public Roads Authority, and the Norwegian Geotechnical Institute. The primary objective of the Clarifier project is to investigate the use of innovative, low-cost and sustainable road construction in peatland using a combination of sawdust and sand embankments to form embankments for rural roads that are connecting, for example, critical infrastructure like upland energy farms. Our project was inspired by 4 60-year-old embankments of sand and sawdust that were constructed on Norwegian peat. Although a range of data from the 60-year-old trial embankment exists, we are lacking detailed data on the failure mechanisms of such sand and sawdust constructions on natural fibrous peat. And as well, we are lacking data on the performance of such embankments during traffic loading. So these 2 items form the main research objectives of the Clarifier project. To meet these objectives, we performed a series of centrifuge tests. So first, we started with so-called free plate loading tests, where we were interested in how well can we model natural peat and how can we investigate the failure mechanism further. So these models consisted of natural peat that was loaded vertically by a load plate. In these models, there were a range of instruments, for example, displacement sensors, pore pressure transducers, total pressure cells, and also we had a CPT to investigate the soil properties during flight. Then we performed 4 embankment tests. These tests consisted of these sawdust and sand embankments at small scale above the peat. And in this test, we investigated the behavior of sand and sawdust embankment during traffic loading. Then we were interested in how is the peat variability, so the natural inherent peat variability, affecting the test results. And we performed one test where we looked at the role of a geotextile at the interface between the sawdust and the peat. On this slide, you see some impressions from our research. So on the left-hand figure, you can see how we sampled the natural peat. This work was carried out in close to Trondheim at the Norwegian geotest site, which is also a part of the Geolab project. So then, after cutting these samples and storing them safely, we transported them with a ferry from Norway all the way to Deltares. There we cut the samples so that they could be used in a plain strain centrifuge model, which you see in the middle figure. And here you can see as well how the sawdust and sand embankments were built. Then this model was transported to the centrifuge, where we performed the centrifuge tests at Deltares. And at the bottom right corner, you can see an image after the centrifuge test was performed. So you can see the sand and sawdust embankment and the peat heavily deformed after failure and much beyond. So we are now working on investigating the experimental data, using the data from our sensors, but also conducting a range of digital image correlation. Then we couple our work with numerical modeling and as well the field data obtained from the 60-year-old field trials to get further insight into the behavior of these sand sawdust embankments on natural peat. If you're interested further in this research, we just published a preprint of our first paper on the behavior of the 60-year-old trial embankments on peat, which you can download already. And in addition, Deltares performed a very nice video which highlights the work carried out in this Geolab verifier project, which can also be found online. Finally, I'd like to thank all the project partners of this Verifier team, then the Geolab project and Deltares for hosting us while we carried out this project. Thank you very much.
Okay, thank you, Stefan. Nice presentation, thank you. Yeah, looking at time, let's move on. The next presentation will be by Giulia Vigiani of Cambridge University on the project called Sand Limit, Centrifuge Modeling of Desaturation for Soil Liquefaction Mitigation. Giulia, go ahead.
Yes, I cannot share because Stefan is still sharing.
Okay, Stefan, please stop sharing.
Okay. Okay. Share. And hello.
Yeah.
Can you see my slides?
It's okay.
Okay, perfect. So, hello, everybody. My name is Giulia Vigiani. I am from Cambridge University. And just I wanted to give a little mention to the fact that in the first round of proposals, we carried out two projects at Cambridge. One of them was this CTP-SSR that was about the cyclic and monotonic loading of piled rafts for onshore wind. And this is the team. It was a completely girls team. So we had two researchers and one intern and so on. And the project I'm going to talk about today is this Sand Limit, which was about the centrifuge modeling of desaturation for soil liquefaction mitigation. Now, although you've heard from Tom that Geolab is about the threats posed by extreme events to the critical infrastructure of Europe, and although not specifically focusing on the seismic hazard, still there are large areas of Southern Europe in which the seismic hazard is very relevant, particularly Turkey, Greece, Italy, and also Portugal. And of course, this is posing very important threats to our infrastructure. So this issue of potential soil liquefaction is a very relevant issue. So the objectives of the project were to assess the susceptibility to liquefaction of sandy deposits to liquefaction under realistic conditions of stress, seismic excitation and drainage, and to evaluate the performance of a mitigation measure, namely induced soil desaturation, to mitigate the risk of soil liquefaction. Now, this is wave-based in the sense that we were propagating S waves and P waves through a sample of soil while in flight on the centrifuge to see whether this induced desaturation was reducing the risk of liquefaction. Now, the team was essentially a Portuguese team. The leader was Cristiana Ferreira, who is a research associate professor at University of Porto, and she was assisted by two young researchers, one PhD student from Iran working in Portugal and one research associate from Colombia, and Professor Antonio Viana da Fonseca, who was the most senior member of the team. There was also one intern, Arianna Pucci, coming from Italy and joining the activities of the team during the project. Now, this is a very experienced team on this topic. They have, both from the point of view of the interpretation of wave propagation methods, both P and S waves, and also the connections between wave velocity, degree of saturation, and risk of liquefaction. We tested two models. They were both created in Hostan sand at a relative density of 40%, and one of them was fully saturated using methyl cellulose solution. This not water. This is to render compatible from the scaling point of view the times in the seismic times, the dynamic times, and the times of consolidation. And the model were heavily instrumented. So you can see that there were three layers of bender elements. These were in the direction, they were propagating S waves and P waves in the direction orthogonal to the direction of shaking during the seismic events. And the models were fully instrumented using pore water pressure transducers, so miniature pore pressure transducers in the free field and close to the bender elements, and piezometric accelerometers. And obviously not shown in this slide, the strong box had a perspex window, so it was possible to do PIV, particle image velocimetry, during desaturation and shaking. And I'm always talking about this induced desaturation. This was created by injecting compressed air from the bottle of the sample in a number of ports. In this way, we were creating bubbles of air inside the soil, and the bender elements would be in regions where the soil was not saturated anymore. And bender element measurements of shear wave velocity and observations about excess pore water pressure during shaking were taken for the saturated and the desaturated models. Now, I don't know how many zillions traces of bender elements were acquired during these tests, and I know from Christiana and her team that they are still busy with the results, with processing the results, but there is very strong evidence that this technique of induced desaturation was very effective in reducing surface settlements and reducing the risk of liquefaction. These are some slides from the actual experimental work. So this is the bender element system, which included the function generator, an amplifier, and an oscilloscope. The bender elements, as I told you, were propagating shear waves in the direction orthogonal to the direction of shaking, and the bender elements were mounted on this perspex frame. You can see here the bender elements protruding into the soil sample. So these were shear waves that were horizontally polarized and traveling horizontally. And here you can see model preparation. So as the sand is pluviated, the instruments are placed, accelerometers and pore water pressure transducers at the different heights in which they are supposed to be. Here you can see the two columns of the frame that are supporting the bender elements. The top of the frame is only connected after the sand is being completely poured. This is more on instrument preparation, and this is a very happy Cristiana Ferreira once the first model was completely prepared. And here you can see the model once it's been placed on the shaking table. So there is this servo hydraulic shaker that can simulate all sorts of dynamic histories. And also you can see here that there are 3 LVDTs that are measuring the surface settlements of the sample directly, besides the PIV, which is done through this Perspex window on the sample. Here is Fausto Molina, still in the centrifuge, but the model is absolutely ready to fly. This is a view from inside the Cambridge centrifuge. And I just wanted to mention that together with this, that were the main activities, the centrifuge testing, there were a set of parallel activities which took place in the geotechnical laboratories of the Cambridge National Research Facility for Infrastructure Sensing, which included sand characterization. So the Hostan sand that was used in the test was fully characterized in terms of particle morphology using a quick pick equipment that will look at the particles as they fall in front of a stroboscopic light, and there are pictures taken. So you can look at a number of morphological parameters, including sphericity, aspect ratio, and the likes. And resonant column torsion shear tests were carried out on the sand, both in dry conditions, in water saturated conditions, and saturated using the same methyl cellulose solution that was used for the actual tests, so as to have a direct measurements of small strain modulus and damping ratio from representative samples of the soil. Now, the sand characterization team was, the sand characterization was mostly carried out by the intern, Arianna Pucci, and by Rashid, the PhD student, who had a lot of fun using the equipment available in the new civil engineering laboratories at Cambridge. And just to finish, this was a really fun example of teamwork. I think that everybody got something out of it. Cambridge now has a system of bender elements that can operate in flight, and we're using it over and over again, not just to look at desaturation effects, but also for other effects. And this was, you know, a first attempt at cooperating with this team from Porto, but it is pretty obvious that we're going to cooperate over and over again in the future, to say that these transnational access projects are often the opening way to put in contact different teams, different research teams from different countries in Europe, and pave the way to very, very meaningful collaborative work in the future. Thank you.
Okay, thank you, Julia. Interesting overview, interesting presentation. We are nice on schedule, so yeah, we go to the last presentation in this section by Stanislav Lennart of the Zach. I don't know the abbreviation, but Zach Institute, University of Maribor. This will be on the resilience of stabilized and conventional high-speed railway track subway. Stanislav, go ahead, please.
Can you hear me?
Yeah, and see the presentation.
You see my presentation. Okay, yeah. Great.
It's okay.
Yeah, so I'm going to present a project which was performed by large-scale triaxial apparatus at Slovenian National Building and Civil Engineering Institute. We collaborate with the University of Maribor in Geolab project. This apparatus is actually the smallest piece of equipment participating in Geolab project, and it's used for technology readiness, the lowest technology readiness levels. It can be used for mechanical testing of various geomaterials. What is it? Its advantage is that it's actually large-scale triaxial apparatus, which can be used in different modes, in triaxial, direct shear, simple shear, and also different kind of custom-made loadings of specimens, also with principal stress rotations. As Ton mentioned earlier, we use it also for small-scale traffic load simulators. The specimen which can be tested is of size up to 80 centimeters in height, 40 to 40 centimeters in square. here are 3 photos presenting different modes of testing. In this particular project, which I will present, University Afton Kosatepe from Turkey proposed testing of railway subgrade to see what are its deformation characteristics. Basically, very simple test. So to what we normally do in small scales, but the advantage and why this apparatus was used is that with this scale, with this size of specimen, we can actually test coarse material like ballast, and that was also tested in this test. So the objective was to do characterization of ballast track, particularly ballast material. What is the effect when it becomes fold? So we tested clean folded and folded ballast behavior, and the final goal is to optimize the rehabilitation work of on old railway tracks. All ballast railway tracks, ballast become dirty with time, and sometimes the railway managers do not really know what is the final level of dirtiness of ballast when it's necessary to clean it, or particularly to replace it. So the work plan has been to perform simple shear test on this particular material with cyclic loading. Confining pressure was corresponded to K0 condition, and the vertical load which was used was correspond to the 22.5 kilonewtons per axle load, which is standardized in for railways for this kind of track, which was analyzed. So 2 real materials from ballast materials from site were used during the reconstruction of one railway track. We got this material. So on the right side you can see clean ballast, and this clean ballast was installed instead of dirty ballast on the left side, which was excavated from the railway track. For installation of specimens, we used more or less similar relative density of both 2 materials. Also, it's clear that densities for these 2 materials are not the same, particularly if we would use optimum density or something what we can achieve with high compacted approach. So that's the apparatus. It's as I said, simple shear mode has been used. Displacement are measured on site, and on one front side of the specimen. As all those LVDTs are installed directly on frames, it's possible to measure very accurately deformation. And the loading procedure which we used is described here in this table. You can see we try to start with very small strain cycles to see what is the response. That's how the displacement increased, and we decided to change the loading rate during the cycling. So with an idea to have approximately the same time for every load cycle. So when we used very small strain, the loading rate was small, while for large displacement, loading rate was increased. On the left side, you can see how the specimen deformed in later cycles. While here we have hysteresis curves for two typical tests. Obviously, yeah, on the lower pictures, we have loading cycles at very small strain rate range, while at the top there is a total loading history for both these samples. So with this project, we characterize deformation properties of two types of ballast. The project was comparing to previous presented project was quite simple and short. In 2 weeks, everything was performed. We observed noticeably lower stiffness of fold ballast compared to the clean ballast, what was also expected. So in this experiment finished just recently, and so further step is to evaluate all those deformation properties and use them in numerical analysis. And the final goal is to evaluate what can be expected deformation properties of such ballast track when ballast is folded. So thank you very much for this opportunity, and Tom, you can go on.
Okay. Thank you, Stanislav. Interesting presentation. Good. Yeah, let's move now to the next part, the next session, which is on 3D high density spatial measurements. So Suzanne van Ekelen of Deltaris will present innovative measurement technologies offering opportunities for groundbreaking research. Go ahead, Suzanne.
Hello, good morning. Do you see my screen?
Yes.
Good. I will be presenting about three-dimensional high-density spatial measurements. I've not done this work alone, not at all. Here are some of the contributors to this story. It is based on reports to be published 9/5, to be published in the end, by the end of the month, as Tom has explained. And the most important message is I'm going to tell about measurement techniques that are available in some facilities. Sometimes the measurement technique has been available, not necessarily now, and in other cases a measurement technique can have been developed recently. So in each case, if you think about starting a project, submitting a proposal, contact the facility early. If you know which facility, then that facility. But if you don't know, if you don't have an idea, then any facility is fine, because they will guide you towards the facility that fits best, and then discuss the possibilities. There are, in most cases, there are possibilities. So this presentation is to give an idea what might be possible, but please discuss it. What are we talking about? Three-dimensional high-density spatial measurements. So that's not single-point measurements, but high-density spatial measurements. So a lot of measurement in a certain space. Two-dimensional can be along a line, or three-dimensional can be the settlements of a surface, or even a full three-dimensional image of the deformations, for example, in a soil body. This row is about deformations. We can also want to characterize a soil body on soil type, on density of soil, stiffness, saturation, or temperature. In former times, we did this with boreholes, taking samples. And now we have techniques that we can use to look into a soil body. And I will show you some of them. So this presentation focuses on the three-dimensional high-density measurements. In this presentation, of course, we have to limit ourselves for now. We focus on deformations and characterization, and I will start with deformations, and then this is three-dimensional PIV and optic fibers. About three-dimensional PIV, this is a major technique. It's basically using photos and then detecting movements in a series of photos. And this technique has been in use for fluid mechanics for over 40 years already. And in the beginning of this century, we started with the geotechnical applications. This part of the presentation about 3D PIV was prepared by Sam Stanier of the University of Cambridge. For PIV, we rely on a good image texture, so we need good photos, and we need to know when they were taken exactly in comparison to other measurements done in the test. And this is not easy. And in the University of Cambridge, they know a lot about this. And you need appropriate photogrammetric models software to make to interpret the results. Recently, 3D applications of PIV has started, and I will show you some examples. One example is this odometric frost heave apparatus. This is not really 3D, it's pseudo 3D. This is in Cambridge, and we have a cylindrical sample, 10 centimeters wide, diameter, 20 centimeters high. And it has a double cell with the internal vacuum to provide insulation, because we have frost heave, so the temperature is very important, and to prevent condense occurring on the glass. Of course, it's frost heave. That means that there will be a very low temperature at the bottom of the sample, higher temperature upper. And then we see that the sample increases in height and ice lenses can occur. And when we thaw, the opposite happens. And they captured the deformations with a single camera. Only you see the camera in the photo, one shot calibration. And they used the constant radius of the sample to calibrate their photos. And that was not easy. It was circular, so things got deformed, and the classical software, OpenCV, did not perform very well, and therefore they have developed new software to compensate for different types of errors, and that reduced the errors a lot. And this research allows new insights into frost heave and freeze-thaw cycles. Another research was originally done by Australian University of West Australia and later developed by Cambridge and ICL. And here we see 6 cameras around the triaxial apparatus. And those cameras, if you look closely, you see a green rectangular thing. That's the Raspberry Pi 0W. And that was combined with a high quality cameras. In this set of each cameras with that Raspberry thing is a relatively cheap thing. So labs can afford to buy several of these things. And this was developed further by Cambridge, and they used an UDP controlled acquisition system, and they are still developing this to be able to have a really synchronized interpretation of the data. This PIV-driven 3-point cloud analysis. And the result of this PIV work is that we have a very, very precise measurement of the displacement, micro precision. Another example is multi-camera measurement of centrifuge sample surface. Again, those screen plates, the Raspberry Pi 0W and a camera array this time. And this is strictly spoken not PIV, but structure from motion analysis. But the idea is the same, and results look like this. So here we see in the right-hand side, the vertical displacement measured with this system. In this case, we have a slope with a pipe underneath. And the 3D surface and topographical measurements were done. These cameras. So this system can be used for other construction modeling, such as tunneling induced settlement too. The University of Cambridge is continuing her developments and to further acquire image synchronously and then analyze multiple image streams. And finally, they will make available simple and open source packages in Python to do this work. So the basic idea of 3D PIV is that we use more than one camera, like the human eyes. Then you can make 3D pictures. In Deltares, this ability was developed too, and in 2012 we developed the possibility to cope with the refraction surface, and that means that we can look through water, and the breaking index of the water is compensated. And a few years ago, we continued with measuring the scour development around an offshore foundation in a lab experiment. And for this, we needed 3 sets of 2 fixed cameras in underwater housing. And then you see we have a perfect 3-dimensional picture of the deformations in time due to scour. So far, PIV. I will continue with optic fibers. And optic fibers are basically used to measure temperature, acoustics, or strains. And here we see strains. You can create a plot, a 3-dimensional plot, both in length, both in time and in length domain. Here we see the development of strains along the time, which is on the left-hand side axis. Here, the time. Now, from these strains, it is possible to determine XYZ deformations, and I am personally very enthusiastic about this new development. The basic idea is to make a combination of several optic fibers, for example, like this. And when we have this combination, then we can determine the XYZ deformation in a soil body exactly. And now for perhaps the project that Mark Schneider has presented, we have used this system. And here we see of the supplier nerve sensor systems. We see a lab version and an in situ version of this XYZ test measurement system. And here we see at the left-hand side a small test setup of Deltares in the Netherlands, and on the right-hand side the larger setup in Darmstadt, which was shown by Mark too. Here you see the piles, and then above this we see sand with this system installed. So here we see the XYZ deformation fibers. This is the final test setup. And here we see, which is important, as we with this system we can only measure the relative XYZ set deformations in comparison to other locations of the fiber, but some reference system is needed to know the exact XYZ deformation. And here we see how we did this. We used cables to measure the exact displacement of certain points of the fibers. This is the result. We see in a sequence of measurement lines of one of the fibers in time. You see it settles and you recognize the locations of the piles. So far, deformations. I will continue my presentation with some measurement systems that are used to characterize a soil body. And I will first go into the word tomography, because there are several measurement techniques that use this word. And this is tomography means this is technique for imaging the subsurface that uses any kind of penetrating wave. So in this picture, we see S1 and S2. Those are tomography images, while P is this not, because this is more a looking through thing, but the S1 and S2 is a cross section made by a certain penetrating wave. And when we have several of these pictures, then you can produce a three-dimensional picture too. So both 2D slices and full 3D images are possible with any kind of wave. There are many examples where that word tomography is used. So like electrical resistivity tomography, ERT, I will show you this, ground penetrating radar, seismic tomography, X-ray, and there are many more. Sorry. The characterization with waves, then we have different types of waves, like mechanical waves, which are seismic or acoustic, electrical currents, then we have transport of electrons, and we have electromagnetic waves, and we will go along these three. So first, the mechanical waves that can be acoustic waves or seismic waves, so moving air or water or moving solid matter. So acoustic waves are used by sonar boats to measure the depth, for example, of the sea where the boat is going. And other applications is another application is shown here. Here, scour around the structure is being measured using this acoustic system. We can there measure scour, but we can also, for example, measure the thickness of a slip layer. Then we use a high frequency to measure the top of the slip layer and a low frequency to measure the bottom of the slip layer. And this frequency is important to be aware when we have a high frequency, then we have a small wavelength. Then we can look through things close by, not so far, but it is very precise. And when we have a low frequency, so a long wavelength, then we can go much further with any system, but it is less precise. So you can look close by and then it's precise, or you can look further away and then it's less precise. With acoustic signals, we can also measure a temperature distribution, which has been used, for example, for storage applications and leak detection. We have done quite some experiments with this in Deltares. And then we continue with mechanical waves, and then the seismic waves, and then the Bender elements. Julia has shown this already. Here we see two Bender elements in the hand of this person, and the application of it in a triaxial test apparatus. And then the Bender element at one side applies a small pulse in the soil with an electric current. So it is a mechanical wave induced by an electric current. And then on the other side, the Bender element feels what happens. And then what we measure is the velocity of the wave and the amplitude of the wave. And here we see the difference in time between the peak of sending and the peak of receiving, the input and the output signal and this gives the velocity of the wave. And then Julia has just shown you these experiments, very nice, in the centrifuge, which can give a picture of the soil body, of the small strain stiffness in the soil body. And at Deltares, we are currently also developing this test setup, or a similar test setup for centrifuge tests. So far, mechanical waves, then electric current and electromagnetic waves, I will tell you. Starting with electrical currents, and that's the electrical resistivity tomography, a well-known technique, applied a lot in the field and also in the lab. We have quite some experience in the lab with using this technique, and it works like this. We have two current electrodes, A and B, and these induce an electrical field like this. And then the resistance between these, the potential difference between these two electrodes, M and N, is measured. And combining these currents between A and B, which we know, the distance between these four electrodes and potential difference of M and N, gives you an apparent resistivity, which is shown now here on this graph. And what is this resistivity? Well, that is a material property. It is the resistance for electrical current per unit of volume of this material. And now in this picture, we see an area with a low resistivity, the upper layer, and a high resistivity. Now, if we move this test setup like this, and then like this, we see in the graph below that we have all the time more or less the same apparent resistivity, which is clear because we have sort of same layered system. Then we move it again, and now we see that the resistivity decreases. And now it is at its lowest because it does not see the high resistivity area anymore, layer anymore. And there it comes back. Now from this, we can determine that this is a good location to take a soil sample. And the results of such an, not the one before, but of an ERT series can be like this. We see a lot of colors with that all indicate resistivity. And here we have a graph that shows the relationships between different types of soil or water and this resistivity. And that's, yeah, there's some choice, as you see. Therefore, it's useful to also have a borehole, which was done in this case. And there we know which type of soil, and so we can make a full profile. The system of ERT gives you a kind of blocks of volume, units of soil that has a certain resistivity. And so you does not immediately look into the soil. You don't have your results immediately, but it is very robust. It is going deep if you put the electrodes far enough of each other. It is very useful, and currently several new techniques using this technique, new test setup using these techniques are under development. Also at Deltares. Here you see such an electrode. It's very important to have good contact between soil and electrodes. Now in the lab, we have measured temperature distribution, and we are developing possibilities to measure PA membrane in the field, and we test this in the lab. Now, electromagnetic waves. Here we see the scales of wavelength, which is related to the frequency of electromagnetic waves. And this is the visible area of these wavelengths. And here we have the other types of waves: gamma waves, X-rays, ultraviolet, infrared, microwave, and different types of radio waves. So radio waves have very long wavelength, so they come very far. And the gamma rays on the other side, they're very small wavelength, high frequency, so they do not go far, but they can give very precise results. Now, LiDAR or scan systems use these frequencies. Infrared is part of that, is there. INSAR or other satellites use a frequency around this. And ground penetrating radar uses frequencies like this. And I will show you one slide about LiDAR and INSAR, and then I will shortly go into infrared and ground penetrating radar. So LiDAR and INSAR are both scanning techniques. We can scan a surface. The INSAR is from a satellite, and LiDAR can be done from an airplane or a drone, or just a 3D scanner in a lab. We're also doing this for PEPSTR, for example. And then infrared. This part was contributed by Barcelona University. The idea is that wet soil has, and the purpose of these measurements is to determine the saturation of the soil. So fully saturated, fully dry, or somewhere in between. And here in the right-hand side picture, we see in Deltare centrifuge test, and we see where the groundwater level is. It's here. You see that this sand, which basically has the same color as this sand, is much darker. And here you see also much darker sand than here, which is the same layer. So wet soil has darker color than dry soil. And why? Well, this is the result of the interaction between light and matter. There's water around the grains, and this changes the scattering and the absorption of incident light. The more water, the more light absorption, both in the visual range, but specifically a lot in the infrared range, and then specifically between those wavelengths. Well, here we see this. Here we see the difference between dry and wet soil. That's only the difference, and you see the difference is higher in this range and higher in this range. This is the wavelength. Now they did very nice experiments. They took dry desert sand and they made pictures using infrared lights. And then they made it wetter and wetter and wetter until it was fully saturated. And you see this is a light picture, this is a dark picture, and we can measure this with computer. That's a pixel intensity, PI. And here we have the normalized pixel intensity. And from this, Parera made a curve, constructed a curve giving the normalized pixel intensity on one axis and a degree of saturation on another axis. Well, this technique is still under development. For example, how usable it is through plexiglass is still to be determined, but it is a promising technique.
We are getting to the end of the session, Suzanne.
Yeah, this is the last subject.
Okay.
The ground penetrating radar. The idea is we have a transmitting antenna and a receiving antenna, and the waves go through the soil and they deflect at the boundaries of the different layers. And this is a nice animation. We see, I go back, there is a difference in the layer, but there's also a pipe. And the pipe is visible in advance because it's conical shape. And the result is what we see here. We see a parabolic shaped thing, which indicates there is a pipe. I will show once more. So these radar techniques, here we see cables and pipes, those typical parabolic shapes in the results. And this is another example for the thickness of asphalt. This technique is quick, very quick. You have immediately results. You can in the field see where your pipe is. Oh, sorry for the Dutch. It's used in roads, levees, and to determine where objects are buried, like pipes and tubes or anchors. I used it recently. It's done on railways also, and we can use this in labs too, and we use the higher frequencies because of the small scale of lab tests. Now this brings us to the end of this presentation, and I would like to repeat the first message. Please contact the facility. If you are thinking about starting a project or preparing a proposal, discuss the possibilities for measurement techniques. I thank you for the attention.
Okay, thank you, Suzanne. Very nice overview. I hope it is an inspiration to the participants to come up with nice ideas, nice proposals. Let's get to the questions. We have a few questions in the chat. Can you, Malika, can you address them?
Yes, of course. Thank you so much. The first question we have for Mark from Daniel. You use a metallic reinforcement. Will you want to use a geosynthetic one? Is it possible to modify the pile arrangement?
Yeah, so I will answer these questions. So for the first part of the question, for the steel reinforcement, so within the scope of PEPSTAR itself, it is not planned to use the steel, it's planned to only use the steel reinforcement. But in general, we are of course interested in the behavior of geosynthetic reinforcements in the same test setup, because when we assess the performance of the system, we would also need a reference so that we can compare it to, that we can actually say it behaves different in these aspects. So this is a goal of us, yes. The second part, or maybe is it answered to your liking? Yeah, no addition, okay. And the second part of the question, the pile arrangement. This depends on how the question was intended. So for this specific piled embankment test setup, it would generally be possible, but it would be a lot of effort. So basically better not do it. But if it was intended to be a question about the geotechnical test pit in general, then yes, of course, there are different configurations possible. For example, in the second round of the TA happening this year, there will be a project with Grenoble and Cambridge, where they take another of these 5 by 5 meter parts of our test pit and install a single pile in a steel cylinder to load it horizontally. So there are lots of different pile radius. I wouldn't say that the pile radius is limited by the pit itself, so it's 5 meters in the one direction, but rather by how much soil you want to model around the piles before you get to your limits. Yeah.
Maybe I can add on that. So Daniel, hi. This is Hauke. So in terms of the pile radius or pile diameter, what we are currently using now for this next round is a pile diameter which has 32 centimeters, so 220 millimeters in diameter. Yeah, and I would say, so typically we say we would not go much further than this, so maybe 400 millimeter, maybe 500 millimeter, but then if you load them horizontally, then you will soon get in an area where you have a boundary effect. Yeah.
Mm-hmm.
Okay, thanks a lot.
Good.
Welcome.
Thank you.
I see now some questions that are directed to me. I found the chat. Yeah, indeed, there's a lot of information in these documents and on the website where you can find just to, if you are considering to develop a proposal, some comments I made can make. First of all, on the composition of the user group. So you usually have a user group leader and a couple of organizations working together. So what we like to see is that there's collaboration with also industry. This is because industry is basically the organizations that really are going to provide solutions in the long term. So if you have industry participation in your user group for submission of a proposal, this is an advantage. Also the involvement of critical infrastructure owners, so basically the end user of an innovation, is an advantage. So an ideal group consists a little bit of that. On the other hand, we have also seen very good proposals by only academia, so that's also possible, right? So that's on the composition of the user group. Then on okay, how much time is available? It depends a bit on the facility, but in general, we can do projects that are like 15 or 20 days in using the facility. And this is not only running the experiment, it's also the preparation, because it sometimes takes a lot of time, the test, and afterwards taking everything out together. Right? So that is then in this period of 15 to 20 days. But that's something also to discuss with the facility manager. So how elaborate do you make your testing program? Do the budgets have upper limits, or what kind of expenses are paid? So what is paid in is the usage of the facility, technical support, scientific support. We do compensate some cost of travel and subsistence. So if a user, 1 or 2 persons from a user group, come to the facility to work together with the team, the local team of technicians for the experiment, we also fund that. And there's also some budget available for hardware. So maybe a soil model or a sensor. There's not a very big budget. So, for example, if you have you want to have a scale model of a tunnel boring machine, for example, we cannot fund that from the project. So you would have to bring such a scale model. Right? That's too much. That would cost too much. And yeah, this basically, I think, what was mentioned before: get in contact with the facility early. That's a good message. Yeah, that's some recommendations I can make on how to develop a proposal. And the proposals that's also a question how to submit the proposal. So we have a template for that you can download from the website, and it's also written there. You submit your proposal to the facility manager. So in Deltare's case, this is Suzanne van Egelen. So she receives all the proposals, and they are brought together for the selection panel. Yeah, I think that's what I can make out of the questions. Oh wait, there's new questions.
It's a question about the definition of a new early stage researcher.
Yeah, this is maximum 4 years. That is correct. We need to use the European definition of an early stage researcher, which means that people that have already reached their doctorate level are not considered to be an early stage researcher.
Maximum 4 years after master's level.
Yeah, after master's. If a person, for example, has worked in industry after master's for 2 years, that can still be considered, and then is working at a university for 3 years, for example, so that would be total 5. Then this 2 years in industry are not counted, so then it's still an early stage researcher. So it's a bit, you have to look it up at the, it's well written down in there's a whole document on the Horizon 2020 website on that. And so early stage researchers is also an advantage if you have them in your user group. And for early stage researchers, of course, you can also make an application to join the next generation training workshop, where we fund the cost of travel and subsistence And also for internships, we also fund there the cost of travel and subsistence for early stage researchers. Then there's a question to Susanne, I think.
Yeah, the
Very curious about-
influence of the stiffness of the fiber optic of the fibers to the stiffness behavior. Let me just read the question. I'm very curious about the experience obtained with fiber optic sensing to measure soil strains in both physical modeling and the field. Could you please comment on the potential impact due to stiffness difference between cable and soil and slippage? The stiffness thing is that's a good question. The company that we work with attached the fibers to low stiffness plastic, so that is supposed to have a minimum of influence, but of course there will be some influence. It's also sometimes you have relatively large strains and then the optic fibers may fail, and therefore they have developed a system where they have put it like this, the optic fiber around a plastic heart, which is relatively flexible. Therefore, it can have relatively large strains and will not rupture. So they are very aware and they can adapt the stiffness of the plastic to which the optic fiber is attached, and they can take measures to prevent rupturing. And then the influence of slippage. I think the friction between soil and optic fiber they have several measures to prevent that it slips. Of course, we want that the optic fiber moves with the soil, and they have there are several measures exist that they stick together. For example, with a rough surface, and in some cases even a feelable ripple between on the surface of the optic fiber product.
Okay, thanks. Are there any other questions?
There was a question about sharing the presentations. I expect that the presentations will be available on the website of Geolab.
Yes, a recording of this webinar and all the presentations will be available, and I'll send out a link afterwards.
Okay,
yeah,
that's good to know. Okay, is there any? No, there's no more questions. Okay, then nicely on time, I think we can close the webinar. Thank you so much for your participation and your questions. Yeah, I hope we'll see a lot of interesting proposals from your side. Thank you for your time, and see you. Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye.
Thank you. Bye-bye.